Thank you, Lauren. And so I wanted to give this presentation in response mostly to members who have been asking what's the status of Crater Lake, where are we at with it. And I don't like to get out ahead of the board of directors with brand new information that they haven't seen and digested yet, but I was getting pinched between the last presentations of the year and some information that frankly we've been waiting on for 3 or 4 months on the geotechnical. So I'll kind of steer away from those details, but still give you an idea of where we've been and where we're going. I plagiarized from a whole bunch of different presentations because it had some of the old and some of the new, and frankly I had about 45 minutes to put it together, so I did a lot of cutting and pasting, but it kind of shows you a little bit of a progression as well. So this slide was actually from a January 12th, 2016 presentation here, and I just repurposed the slide. So this is Crater Lake in the winter, and you can see that even in the middle of winter there can be some water flowing out of it. And what I generally do is kind of wait till the end for questions, but we can be a little informal, and if something's really itching at you, I'd rather you asked it right then than forget it, So go ahead, feel free to break in. But basically, this is going to be mostly a presentation of the reasons that Cordova Electric is interested in pursuing this project. And so what you're going to see is a lot of the positive aspects, a lot of the reasons that we would want to develop a project like this. And I really don't touch too much on some of the downsides and stuff. So I encourage a lot of audience participation. I may move fairly quickly, but I'm hoping that there can be some questions and interactions at the end as well. But really I wanted to kind of just bring you up to date on where we're at with it. So I thought about staying away from the technical side and maybe the operational side and just focus on the economics, but that's not why we're looking at the project. Those operational and technical aspects of the project are important in the big picture of energy and even in our local economy. So I think it's a disservice to leave those off the table. And then I want to talk about what we've got invested to date in the project, how the concept has changed, if any, and what the last step we took on the project was and what the next step would be. So these are some older slides that we kind of started back 3 or 4 years ago with, but basically the project is looking at both water and power. And on the water side, Crater Lake's a very clean, reliable water source because we can store a lot of it, and it's high in the mountains, so there's very few organics. So it would require lighter treatment, and it would be a big storage vessel basically that we don't have to worry so much about drawing on emergency supplies. It's not the only way we can manage water shortages, but it's one way. And it was actually the city looking for alternate water sources that got me to circle back and take a look at Crater Lake as an energy resource, and it was a lot more attractive than I'd ever envisioned. Oops, probably pointing in the wrong direction here. Now I'm going the wrong direction. Okay, there we go. I should probably touch on this as well. So most of our diesel energy production happens in the winter, but some of it happens in the summer. When you can store a renewable energy resource in a dam, you can shift it over a whole season in a storage vessel as large as Crater Lake, and the same with the water. So it's available when you need it, and you can even carry it over from year to year. So the benefits, as I mentioned, it's the highest quality source in the whole city regime. Crater Lake could double or triple the overall water supply that it's delivering to the community now, and the size of the water lines and the power lines that come in from Crater Lake now are adequate to bring the additional energy, so we don't have to do a lot of transmission line infrastructure upgrades. Right now, I mentioned that we can have lower chlorine levels at treatment. There just isn't as much organics in the water that needs treated, and the city has switched to ultraviolet treatment. They purchased a lot of additional capacity out at their Crater Lake treatment facility, anticipating that this project might come along, so they would have the ultraviolet treatment available to handle larger volumes of water and a bigger year-round supply. It would reduce the overall maintenance and effort of the water supply, and I'll show you one of the reasons why. And it would build onto the existing water system. That's the transmission part that's already in place.
Lake,
Yes.
would they still then be using chlorine in addition to ultraviolet?
My understanding is they would still use a little chlorine. I think they said they could use like a fourth as much, but it sounds like they'd still use some chlorine. It just wouldn't be nearly as much. It's a good question. So this is the existing Crater Lake water supply. It's just a really rudimentary catchment, and you can see that it mostly fills with gravel, and it has to be hand shoveled out a couple, 3 times a year. The infrastructure is in fairly poor shape, but this is a really maintenance-intensive beast. And depending on how the responsibilities shook out, if it was a city and Cordova Electric partnership, you know, the costs and the maintenance might land on Cordova Electric, because we kind of operate water systems like the city does. But essentially, the maintenance would go down pretty significantly on a day-to-day basis. So on the electric energy side, stored energy can be used when it's needed most. Another way of saying that is if we have 2 million kilowatt hours of energy in Crater Lake, which is about what we have, we can strategically use that against our diesel loads all the time. So it can pretty much all offset diesel, because it just so happens that the times when we need energy are almost exactly the times that we need water. When fish processing peaks, so does energy needs. When our water supplies start freezing and drying up, that's when we run out of run-of-the-river hydro, and it's when the city runs short on water. So the availability of water and the use of water are very, very similar with between energy and one of the biggest criticisms I've heard at Crater Lake is it can't get us completely off of diesel. So it's a huge expense, a huge investment, and if it only takes a bite out of what is remaining of our diesel and doesn't get rid of all of it, that's an awful big investment to not get us completely off. But what Crater Lake does help do is pave the way to get off of diesel, because, and I'll talk a little bit more about this later, but when you have stored energy, keep pointing in the wrong directions, right? When you have stored energy, then your intermittent renewables like solar and wind and tidal, for instance, when you can't time those, or when you don't have enough from those to meet your needs, then you can draw from Crater Lake. So essentially you use it like a big battery, and that's what Kodiak's doing. When the wind blows, they use the wind. When it doesn't, they use their Terra Lake project, and that's how Crater Lake could work. So those 5 to 6 megawatt hours of diesel that we still have left, Crater Lake can only meet 2 megawatt hours of those, but the other 3 and 4 can come from other resources. Right now, today, I was just texting the crew, because I'm pretty sure that we're 100% hydro and we're spilling extra right now. And that also makes it hard for some of these other technologies, because if we install a solar plant and we're spilling water half the time, that makes it really hard to get that solar plant to its full benefit and usefulness. So that storage in the system is what helps you do that at times. So I'm sure most of you know where Crater Lake is, but this is just a review. It sits perched right above the community and Orca Lodge, and this is another interesting perspective. It also sits right in the middle of our electrical grid. So we've got Humpback Creek out here north of town, a submarine cable to Orca, around to our diesel plant, the community, and then out to Power Creek. So this was the number 3 years ago, about $20 million for Crater Lake. Small dam, well, different sizes of dam. You can see it could stretch clear over here, or it could be a smaller footprint. That changes how much the water elevation is raised and lowered, how much can be stored. This is a proposed pipeline routing. If anything, this might end up coming over more this way instead. That's one of the options. It's becoming more likely, because Shepherd Point Road, I think CEC is fairly agnostic overall to how that might impact Crater Lake. But if that does happen, it's important that we plan ahead with them so that we don't duplicate or get in each other's way, especially if the timing's different. So we've been trying to handshake real closely with that project so that if they do go forward, that we just can keep one footprint and try to share cost rather than cause cost for each other. And this was came out of an engineering feasibility study that we did a couple of years ago. It's posted on the city's website, in Cordova Electric's, I believe. So some of you saw the battery energy storage presentation a couple months ago, and I wanted to do some comparisons about costs, but they're two completely different tools. And I think I've had the question a lot, well, why not just use battery energy storage instead of like developing a hydro? Well, that's really not, excuse me, that's not where a battery shines. So this size of a battery, a 20-foot container stacked completely full of batteries, 38,000 pounds worth of batteries, can store 1,000 kilowatt hours. So that's about what a home uses in 2 months, to give you an example. So that is 1 megawatt hour. Crater Lake can store 2,000 megawatt hours in a year. So Crater Lake can store as much kilowatt hours as 2,000 of these batteries. This battery's about $2 million all in. Crater Lake's about $20 million all in. And you say, well, why would you want a battery? Well, that's not why we're getting it. We'll still use it to store energy, but what we're really using that for is the power capacity in it. We're deflecting a whole bunch of water at Power Creek right now to balance our system, so that if somebody puts a load on, those deflectors can pull out and deliver more power. Well, if we have the battery do that, we can pull those deflectors out of the stream at Power Creek, and it's like getting a free 500 kilowatt hydro, and it uses infrastructure we already have. So for a fairly small cost, we get a whole bunch more out of Power Creek. So this is a really good investment on the front end, and we think, and we've got some great partners. And at this point, I would like to introduce Rob Hovsapien and Maya Panwar are in the project leaders for our grid modernization project, and they're in Cordova for our technical interchange, quarterly technical interchange meetings. The rest of the crew will be getting here, so and I hope they ask some really pointed questions as well, and call me on anything here. But so that's the difference. Is a battery is a tool, but it's a different tool than energy storage. And so this is another little bit of insight into the differences between storage, and also some of the operational costs and operational advantages of hydro. So in round numbers, diesel drives about 70% of our maintenance cost in our power production department. So over 2/3 of our maintenance dollars go to our diesel plant, and only 25% of our energy comes from the diesel plants. So lots of moving pieces, lots of fuel handling and fuel containment. There's all kinds of pumps and injectors. It's just a lot of moving parts, and they break a lot. And even if they ran perfectly, every 30,000 hours, you're about, depending on the size of the generator, you're from $300,000 to $750,000 into, or $300,000 to about $500,000 into a rebuild. So that's $10 to $15 an hour just for rebuild cost. And this also leaves out some costs like lube oil and some other costs. So basically our diesel cost us 40 cents a kilowatt hour, and our hydro cost us about 6 cents a kilowatt hour. So if we can spill that, if we can store the hydro that we're spilling now, whether it's 1 or 2 or 3 gigawatt hours, then that can take another big huge bite out of that. So we're going to use the battery for some of that, but we'll also use our dam storage for some of that. So hydro has one of the advantages of solar: very few moving parts. It's basically one giant moving part that's bolted together that rides on 2 or 3 bearings, and then there's a couple of gates that move in and out. It's very, very simple. So is there any questions so far? Okay. So I want to wander into technology a little bit, because this is where I think some of the opportunities for hydro that have maybe been undervalued in the past on our own grid, but also on the national grid, is really starting to rear its head as we get more and more wind and solar on the grid especially. So some of the traditional uses for hydro, in fact, some of these were actually more important than the energy itself when they were first built. But flood control and drought control, so reclamation and conservation, water conservation was a big driver. But now we have some, and I want to remind one of the aspects, one of the attributes of hydro that's really attractive compared to other energies is when you build a dam, you're storing water. And in my crystal ball, the availability of clean water going into the future is going to be important, increasingly important. And it doesn't store fuel or chemicals like the other options. It's a simple thing, but it's an important concept. And the other aspect of hydro, I'm not sure I've brought this out in other slides, is a security aspect. If we have 2 gigawatt hours of stored energy, if we lose a fuel supply, if some disaster takes out our other hydro projects, this would likely be the most hardened of our projects in terms of earthquake and tsunami resistance. So if you have 500 million gallons of clean water available in a standalone project that can deliver 3 or 4 or 500 kilowatt hours of energy, or kilowatts of energy, you can run Cordova on a starvation diet for a year on that one project, and that's important to me. And I think it's been important to Cordova Electric in their history as a cooperative, because self-sufficiency is one of the reasons we went to underground power lines, and security and independence is important. So some of the newer concerns that are starting to loom that hydro happens to be very attractive for is a black start. So if your system goes black, what we do right now is a lot of times we use diesel to restart our whole system. You have to get one unit somewhere in your system running and stabilizing and energizing the grid before you can bring something else on. Well, we've had outages in the past where our air starter failed, or an air compressor fails, or a fuel pump fails, or something. But again, hydro is so simple, and it has all that potential energy just sitting there ready to start spinning that thing. Historically, you can literally open the hand wheel, let that energy hit your project, bring it up to speed, and run it. And those mechanical controls are very inexpensive. So it's very easy to put a fully manually operable control system in a hydro, and then you start thinking about things like cyber black start and electromagnetic pulses came up in the last battery presentation. What are you doing for electromagnetic pulse? If you lost all of your electronics in your system, whether it's a cyber attack or something, how could we run? The answer is, right now we have one diesel generator that is so old and has so many manual controls that we can still operate it. We were in the process actually of automating that with new electronic controls, and we've rethought that now. Not only do we not want to have that expense if we don't have to, but if we keep one of those assets in our fleet that we can black start or cyber black start, that's a nice thing to have in our back pocket. So batteries are often referred to as a Swiss Army knife on an energy system because they have so many great things that they can do, and I'll explain that in a minute. But if that's what a battery looks like, this is what a dam looks like. It has even more, and I'll explain that a little bit. So this gets a little technical, but what this is the time scale of things. And I'll show another slide right after this one that explains, has an analogy to the human body that I used in the battery presentation a couple months ago. But so down here on the really super fast scale, this is nanoseconds or millionths of seconds. That's kind of a level in an energy system where one of the advantages is some of the new batteries, they can be super fast. They still use electronics to turn on and off and to go from delivering power to charging power, but they can do it really fast. But they can't do it as fast as a hydro because it's already spinning. Electricity is mechanical energy, and so you've heard the term brownout. What causes that is if you have a generator spinning along at 60 cycles per second and it starts to slow down, the old incandescent light bulbs, as they lose voltage, the amount of light goes out, so you take a brownout. That doesn't happen if a solar panel trips off or if a wind turbine trips off. You go black like that. So you don't have what they call rotational inertia. You don't have a big freight train moving down the tracks that you can slow it down, but you're not going to stop it right. That's how a hydro or a diesel generator is spinning along. It turns out hydro has a lot more rotational inertia. So that means that you're not going to speed it up or slow it down, so it becomes the giant shock absorber for your whole energy system. So when a wind turbine starts going from 500 kilowatts to 1500 to 500 and back in a gusty situation, that hydro is sitting there just taking all those bumps. It's kind of delivering and absorbing that extra energy on your system. So it becomes a shock absorber for your system. So anyway, as you break all this up into different time scales, you see different things happen in different places. So you have high-speed switching devices down here. You have, this is the speed that your protective devices, that they have to, if you have someone grabs a hold of high voltage, you have to turn that off as quick as possible to try to save their life. So we have these devices that operate real quick. Then this is where we talk about those deflectors moving in and out of the stream to balance our system power. Now you start getting into just fractions of a second or somewhere around a second. Now when you start talking about wind and solar variation, that's anywhere from seconds to minutes to hours. You can have a big cloud, fast-moving cloud go over a solar farm and take it just to almost nothing. And this is what's been causing a lot of outages in grids like Hawaii, where they have lots of solar penetration, wind variations. And then you start looking at the kind of scales that you have, outage restorations from storms and whatnot. And then you get clear up to the national grid, where they have to forecast out in advance tomorrow. What's tomorrow's load going to look like? What's the temperature and all the drivers? So different technologies can meet different needs, different time scale needs for energy storage. That's where this is going. You need storage in each of these different cases. The hydro can provide all those. Hydro has everything. It has a rotational inertia that's all but instant, even quicker than these things. But then it goes clear up to years, right? You can, once you have it in your reservoir, you can deliver that energy 3 years from now. So it's the only thing that can really span the whole gamut. So the, did I leave a slide out? I did. Or I put it in the wrong place. Okay, so the analogy in the human system is that that rotational inertia is like glucose. You know, that's what your body, the fuel your body runs on. If you run out, you're going to hit the ground in a couple, 3 seconds. And then you have like carbs and stuff that you've eaten that can quickly be converted to glucose, and that's a quick burst of energy. And then you have the stuff in the refrigerator in the pantry that you can go grab whenever you want and eat it. And that's kind of an analogy to the short-term and long-term storage. And different technologies work for different types of storage. So the battery, it turns out, is more like carbs. It can, and it can also be more like, it can be like glucose and carbs, but it can't take a whole bunch of energy and shift it from January to, July, or vice versa. So these are some of this is one of the considerations that we've been contemplating or taking a look at recently. And Crater Lake has about 220 acres up here, and that's what feeds into this roughly 500 to 600 million gallons of water a year is what that collects.
It'd be good to mention that this hasn't been presented to the board yet.
Okay, well this slide was, but this was, I brought this up at the go, no-go, but I did add these numbers in here. So this is what we would call open loop pumped hydro, and the idea is that if you have a watershed over here, you can see the size of this watershed is fairly close to that one. So these are not exact numbers. I did a fair amount of math to come up with this using just conventional losses and everything. But pumped storage right now is essentially, it looks like if you have a lake down below and a lake up above, if you want to, if you have some excess solar, say, and you want to have a way to store it, it turns out pumped hydro is a very inexpensive way to do that. You run some pumps up through a pipe, and you pump it up to a higher elevation, and then you wait till you need it, and then you let it go back down through the pipe. But your round trip efficiency is somewhere on the order of 80%. You lose water from evaporation, you have some losses when you're pumping, you have some losses when you're generating, so 80% would be a pretty aggressive. But it's still better than having it go to waste, right? But and that's what you call a closed loop, because it's all going through one pipe, and you're pumping the water up and you're pumping it back through that same pipe. So an open loop is more about gathering water from an outside source and bringing it into your system. And the advantage of that is that, for example, here you have, let's just call it 50% as much water as this watershed here. And this comes down and collects in this little basin here. Well, if you put a small catch basin and a pump and ran it over to this lake, what happens is you're taking water from a high elevation and you're using a certain amount of horsepower to pump it up here. But then once you use it, you're running it all the way through a pipe down to a powerhouse down here somewhere, and you're getting much more energy out of it than you put in. even after all your losses. So say you lose 20% pumping and evaporation, say you lose 90% running it through your hydro turbine, but if you're pumping it from 900 feet of elevation, and you're only going up 600 feet, then you got 600 horsepower in, and then dropping at 1,400 feet, getting 1,400 horsepower out. You take those losses out, you're actually getting 1.3 kilowatt hours out of that for every kilowatt hour you put in, and you're grabbing a couple 100 million gallons of water and putting it into your system if you're looking at bulk water sales or bringing more water in through the system for winter seafood processing. So a small incremental cost for a large overall energy gain. And then when you're getting that kind of a gain, it doesn't matter if you're doing it with diesel or whatever. If you can put more water into your system anytime you can, it's good to do it. There's no way that we can, with any conventional technologies, we can hope to get a 30% gain in diesel efficiency. On the other hand, if you're spilling some hydro somewhere else and you've drawn the water out of this, then you can use that hydro you're spilling and actually gain on the amount of energy. So looked at a couple other little polygons here. This is a little farther down, so you're not going to get as much gain, is all I'm trying to illustrate. I haven't even run these numbers. These are just kind of conceptual, just kind of eyeballing the different elevations. So you can get a little more water and a little better efficiency. And then down here, you're getting to the point where your losses, even though this might be 100 feet of elevation above your plant, you're still going to have a loss of efficiency because you're pumping all the way up, bringing it all the way back down. What you're going to gain, though, is a whole lot more water out of the watershed. Probably as much or more than Crater Lake put together. So, not something we've evaluated in any kind of detail, but it is, there have been projects built like this, and it's pretty compelling because if your overall investment goes from $20 to $25 million, but now you're producing twice as much power and maybe half again or twice as much water, then you're just getting more return on your investment. More detail than I gave the board for sure, but that's a thought process. So this is what have we done to date? So these are our overall cost to date, and we were just doing some accounting, so this is just the last couple of days. And these pieces are really firm. This one, maybe not as quite as spot on. I know this is how much we spent all in, but this project, I think we didn't quite spend that much on geotechnical. I think some of this is admin costs and some other costs we had through this process.
Cost to date on what, on this?
Okay, yeah, so the Crater Lake project. This is our cost to date going back to about 2013 when we first started looking at it. And that's just CEC's cost. We got $50,000 from the city here when we worked on the feasibility, and then we got $100,000 from the Department of Energy to assist with our geotechnical assessment. And then the Native Village of EAC was doing a lot of drilling, and they shared their equipment at no cost to us. And so we came in significantly lower on this project than we had estimated. So that's kind of where we're at, and now it's in front of the CEC board to get this final report and see what it means for the project. Frankly, the quality of the rock was a lot poorer than we expected. So what that really means is it's going to cost more to have the same quality of dam there, and how much more we don't know. I hate throwing numbers out. It's not going to explode the project cost, but it will run it up, and it introduces some risks. We have this report, we've exchanged final drafts. We're just waiting for the contractor to get that in. Almost any day I expect to have it. So we hope to have it with a couple weeks time to circulate it to the board and staff review it as well, so that when we have it on the May agenda, they've had a chance to look at it first.
So Clay, can I just ask, since you have this up here, you said you got 100 for that geotech assessment phase. You got 100,000 from the Fed, from Department of Energy.
Yes. And
the other 253, did that come from CEC?
Well, this is CEC's cost, so that 353,000 is CEC's cost.
So, okay, so there could be so that phase would be 453,000 with the Department of Energy money.
Yeah. The total cost was closer to 400. Actually, I think our cost to date was about $318,000, and I think we have just a little bit more for the final report. and then the Department of Energy was $100,000. And our estimate going in was $500,000 for the whole effort, and but we were able to get some cost offsets from the helicopter type in particular. And so then the next step would be a final design. That number I think is probably on the low side, partly because 3 or 4 years has gone by, and it just depends on what they're tasked with. So the reason this was a step that CEC wanted to take is we're trying to push this project to refusal technically. If there's a fatal flaw and we really can't move forward with the project, we'd like to know that so we can set this aside and move on to the next option. And so that's just a process we call pushing it to refusal. And the geotechnical is a point where if there's fatal flaws in the rock, that can be, so we look at the surface and do our evaluation, but until you actually drill cores down and see what lies underneath, you really don't know what you're up against and if the project can be viable. So where are we now? So over the last couple of years, we've accumulated some safety concerns and lots of other concerns, frankly. The aesthetics, the need, the cost. The city, I think, is, in our picture, is much less likely that they would be a full or maybe even partner in the project, just because of financial constraints and maybe other priorities. There has been interest in bulk purchase of water, and we have had some interest in the Department of Energy funding some of the technical aspects of the project that maybe haven't been demonstrated yet. I kind of downgraded this funding climate from good to fair. I think there are some opportunities out there because of some of the opportunities we have with this project, but I think the overall funding climate's pretty poor in terms of grant funding at the federal level, although there have been a rash of really big bills, funding bills lately. The permitting is real important in any hydro project, especially small one, because it can layer a lot of cost and schedule delays. The permitting for this project is very, very, very minimal, actually. So the geotechnical work has been completed. We're awaiting a report. Shepherd Point, frankly, it can drive cost up on this project, or it could offset. I really don't have a clear picture with it, which it just depends on when they happen, whether or not there would be close cooperation, or two projects going their own paths. Where we're really at right now is evaluating the information that we've seen from the geotechnical, taking a look at what the competing options are for us to meet our goals to get off of diesel, and decide at the board level whether to proceed to the next step, which is design. And the way that looks from this other graphic is, this is a process that we try to use to keep the board in front of the project and making decisions before we start accruing all the expenses. And the decisions are, do we move ahead? Do we take an off-ramp and set this project aside? Or do we need more information before we make the decision?
Like, what are those offshoots?
So those offshoots are kind of the brackets on what the cost might be. And what I'm trying to demonstrate there is that the closer you get to the finish line, the more certain your costs and risks are going to be, because you have a little more clarity at each step. So at the reconnaissance level, you really don't know anything yet. You say, well, it could be a very inexpensive. You could be able to put a very small catchment there and a pipeline, or it could be extremely expensive. But once you do that reconnaissance work, that's kind of what we said. We said this thing is, we need to know a lot more before we can narrow that down. Once we did the engineering level feasibility study, it's looking like, well, there's actually a rationale. The estimate is $20 million, but that's plus 20% or minus X percent. So it gives you a price range. I think it was actually $17 million. The $20 million came from CEC's costs, project management costs, and admin and stuff. So that's how you get that range. At the geotechnical assessment now maybe it's looking more like 18 to $27 million, for example. So it narrows, and that's what I'm actually showing there. I kind of expected that this isn't a realistic number. So we think that it's going to be more in this range than that range, and we'll tighten these up a little bit. Then the design, you have a whole lot more, because you basically have it 80 or 90% design. You've already got quotes on your equipment, so forth. Try not to over-answer those. So yes, Kelly.
I have a question.
Yeah.
Well, first, thanks for presenting all this information. And you really don't have to convince me or probably anybody else here on the benefits of hydro generated power or the storage of clean water. The principle, I think, is sound, but I have a problem with this location of the project. Can you back up a couple slides to
You
the
bet.
one that shows the photograph?
Yeah.
The overhead?
Oh yeah. Oh, I'm sorry. That one or towards the beginning?
That's the one right
Okay.
there. You can see my problem. I've looked at the USGS map for the contour lines, and way up there is Crater Lake, and a little bit more to the left and down is where the drain. Nope, it comes right down here. It's where the drainage is,
There?
and it comes right down here.
Yeah.
This is Crater Creek, and this is the Rainey's house,
Mm-hmm.
and this is the creek, and this is their main lodge.
Yeah.
That seems to me to be a real problem. I mean, there's a lot, of details that I don't really understand. But the location of the project seems to be a hazard to me. I know water runs downhill.
Mm-hmm.
This is very untechnical. And I know it goes as the lowest spot. And dams are built at the lowest spot to collect the most water.
Mm-hmm.
And if anything can go wrong, it will go wrong. It's just a matter of time. And when it does go wrong, it's going to be potentially catastrophic. And that's my problem with the project. I have no problem with hydropower. I have no problem with clean water storage. But the location of this project just scares the shit out of me. I should probably not be addressing that to you and to the board, but this is one thing I've not heard about. I've only heard about the upsides to the project, but none of the downsides. And this seems to me to be a pretty obvious downside.
Yeah, so, I'm not gonna argue there's risks with any project, and Lord knows Cordova's been on the, losing end of other types of spills. That's it, there's risks, there's lots of dams in service, they range in risk. One of the advantages of Humpback Creek, for example, is nobody lives below it, and it doesn't store a bunch of water. So, that's a very real risk. I mean, you're storing an extra 200 to 300 million gallons of water there, and if something bad enough to release all that at once, it's going to be a lot worse than what would come out of the lake.
Something
naturally.
can go wrong, it will. And again, I'm not opposed to a project of this nature. I'm opposed to the location of this project. If you were to rearrange it in some way where the water from Powder Creek was directed over to a catchment in the red area over there, where if there's a catastrophic outflow there, it would wash down into the middle of nowhere, into the ocean. But pumping water back up into Crater Lake to make it even a bigger potential catastrophe just seems inappropriate. I mean, I think the risk is too high.
Okay. Over here and then over here.
Yeah, I think that, just to confirm what Kelly was saying, I think that slide shows that Orca Cannery would be a great risk if there were earthquakes, for example, which we know there will be, or other things. But I think that's pretty obvious that becomes a risk. My question is, with Humpback Creek, where we already have a footprint, and is there in the topography there or the canyon in that area, is that a place where a reservoir could be created where there's already a footprint?
Not exactly where the project is. There may be a storage option upstream.
That's what I mean, yeah.
The topography isn't as attractive there, or the geology, but there's potential for some storage. The problem is to get a large amount of power, you need one of two things: either a very large volume of water, or very large elevation, a lot of pressure. So Powder Creek has the volume, Crater Lake has the pressure, Humpback Creek has neither. So to store the amount, even if we could store every single bit of water available in Humpback Creek, we're still only looking at 5 or 6 megawatt hours through the existing system, and we're already getting 3. So we would have to build a whole storage element of that project to get maybe 2 or 3 megawatt hours, maybe. The other thing is Humpback Creek's a very productive salmon stream, so we're not going to be able to shut off flows to that and store water now. Now that can give you some help too. I mean, that salmon run on the even year is basically destroyed now from the 2006 flooding. They have not come back since because a whole watershed scoured out hundreds of thousands of yards of gravel. So a dam might have helped with that, or it might have just filled with gravel. I don't know. But so I think the safety aspect, I do want to mention a couple things. I mean, I don't want to start an argument, but I do, I guess, want to share my perspective on dam safety and the trade-offs. So this historically, Crater Lake historically has developed ice dams. So I want to see if I can find a view where you can see it a little better. Wrong way. Oops. It'll take us right off the map there. So it's a very narrow outflow, and it's about 15 feet deep. So periodically, maybe once every 30 years, ice dams that outflow, and it holds water back, and then it breaks and floods. So I had a friend that was staying at Orca Cannery in 88 or 89, who was sleeping in the bunkhouse the last time it broke out, and they thought the whole place was going to wash away. So that's a, at least in recent history, somewhat frequent occurrence. So a dam can mitigate that, right? Put a dam in place, you don't have to worry about the natural ice damming that's occurring there and the flooding that can happen from that.
Although then, when you had a catastrophe, it would be order of magnitude
Bingo.
worse.
Exactly. That's the
And
trade-off.
that's what I find alarming about that, is that's a total sword of Damocles hanging over Orca Cannery.
I would, if you go Google like Sitka Blue Lake and look at the size. So one of the things about Crater Lake, we're talking about, at the most extreme case, say a 30-foot high dam. So 2 feet of water develops 1 pound of pressure per square inch. So that's 15 pounds of pressure pushing on that thing. This one thing about the rock there is it's a glacial cirque, so it's had 10 times that kind of pressure of glacial ice pushing against it. So we know the rock is fairly competent against pressure just because of the geology of what's there. But the fact that we're only putting 15 pounds of pressure on it is in itself a mitigating factor. And when you look at how dams fail, whether it's earthquakes or whatever, the whole plug just doesn't pop out like a cork. That concrete can fracture and shatter and do all kinds of things, but it's still held together by concrete and steel, and the water filters out, it flows out, but it's maybe not that we would expect. Now there's earth-filled dams and failures that you can go look up on YouTube and stuff where it does have that kind of event, but that's not a concrete gravity structure.
Well,
So
the corollary to when something can go wrong, it will go wrong, is if something can't go wrong, it won't go wrong.
Yeah.
You won't have a dam failure if there's no dam.
Yeah, but you could have a lake failure, right? I mean, if we had a big earthquake and the ground split open, you still have 300 million gallons of water in there.
CEC and the city has no,
It's been there for
hand
millions
in
of
it.
years.
Mhm.
You say that.
What's that?
It's been there millions of years, right? It's still there.
Yeah. Well, I don't know about millions. So there was ice there 10,000 years ago. It looks pretty clear that the lake elevation has been quite higher fairly recently because you can see the old, moraines and stuff there. But anyway, I think we agree though that there's trade-offs. The higher frequency, maybe lower risk events, or probably could maybe happen less if you have a dam there. But you're storing a lot more water, and if something does go bad, it's going to be a lot bigger bad. And I don't disagree at all. So, I'm sorry, question, yeah.
Yeah, it was, several years ago, you were looking at that stream up by Nelson Bay or by
Yeah.
Shepherd Point for, potential hydropower with storage. And I understand that the costs, going from that location are probably quite a bit higher than the Crater Lake proposal, but is that thing still out there? Is it potentially developable still?
So what
You did
we,
some permitting for it, didn't you?
That's a good question. So we got some temporary use permits to put stream gauges there to measure the water resource. So it's it's a fairly attractive site. It's a big basin, and there's about a 250-foot notch in the rock there. So you could build a much higher dam and store a lot more water. Really, it's the development cost. It's a much bigger project, and access is a much bigger constraint. Whereas Crater Lake's on the road system, that helps kind of mitigate your construction risks. So at the end of the day, we got kind of I would say it was halfway between a reconnaissance level, which is kind of me going out in the field and crunching some numbers just based on the water and whatnot, and throwing some assumptions in, and an engineering level study where they actually do a fairly. So we had a firm go out there, basically just gratis, and walk the ground with some geologists. They came up with a pretty solid, if not engineering level, close to it. And basically what they came up with, and this is about 2010, 11, is that it looked like a $150 million project if you had to develop your own access to the site, and it looked more in the $75 million range if you had better access to the site. And one of those accesses might look like the small road that we developed up to the intake at Humpback Creek. That whole Humpback Creek basin has about less than a 10% grade all the way around to that Crater Lake basin. And the last piece is a ridge.
Crater Lake.
What's that? Snyder Falls Creek, yeah. So it goes all the way, it circles all the way back to Snyder Falls Basin. And if you punched a tunnel through that last bit, you can actually drive into the basin. So that kind of access where you can actually mobilize stuff from town to the construction site would cut it in half. The problem is we don't sell enough power to amortize $75 million of debt, and it doesn't provide water to the community, which is the other concern for Crater Lake. So what we did is we just packaged that and said, let's take another look if and when access happens. If Shepherd Point goes through, then maybe we dust it off and take another look. So
if such a big part of this project, or the attractiveness, or maybe the imperative of this project is water supply for the city, why isn't the city ponying up, bond issue?
I think because we've run short on water. They've asked people to conserve and whatnot, but we haven't had to shut anybody off yet, and so it's just not a huge priority. I'll be honest, I think there's other ways to manage our water needs with what we already have, but I think a lot of it too is just the funding. It's there's the city's number one priority is waterfront, getting the harbor back into shape, and trying to create more opportunities for just moorage and business on the waterfront. So, Wendy, did that answer your question? Or?
It just seems like the project is sort of being, I don't want to say sold on this basis, but it's outlined that way. Okay, it benefits the city for water supply, and it provides hydropower, and so why isn't the city right there with CEC and co-funding it?
Yeah, I don't know. Different culture. We think in terms of decades, and we look out 50 years for a hydro. I think the city looks at from budget cycle to budget cycle, to be honest. So, Wendy.
Yeah, Wendy Rainey, I'm actually the fatal flaw here. So my question is, really nothing new's been presented on this. We're waiting on the geotech survey. When is that going to be presented to the public, and when are we going to see that, which is the reason why it may fail, besides the fact that there's life and property at stake? There's a fault line in the center of that, an active fault line. There's rock issues that have been on record for years on the bank stability in that area. When is the geotech survey going to come out and be made public, and we have a serious conversation that isn't a salesman telling us that this is a good project? The city said flat out in a city council meeting they do not need the water at this time. That's why the city is not backing this project. Also, there's life and property at stake for city members. When is there going to be a presentation that puts the whole thing on the table so that people in the community can see what the big picture really is?
Well, so our geotechnical report was actually supposed to be delivered by the end of December. The earthquakes in Anchorage didn't help because basically all the geotechnical firms had to pull off whatever they were doing and do school and ground assessments and so forth. We did get the final draft, and just our design engineer looked at, who have geologists on staff, have interpreted the I would say raw data or the field data. So basically you have a geotechnical firm, and they go out and they pull the core samples, they characterize what they saw on the site, then they do a bunch of physical testing. They do acid tests on the rock to see how is it going to stand up to just the acid in the rain, for example. They crush the samples of rock to see what's the hardness and strength of it. They tabulated that into like a, I don't know, 100, 120, 130 page document. So our engineer reviewed that. I think they got it 2 or 3 weeks ago. I hope to have it for this presentation, certainly hope to have it for my board, but I didn't. And so yes, there's not a lot of new information here, but I have lots of questions from the public on where you're at with Crater Lake. So I wanted to give an update. Unfortunately, it just doesn't have the geotechnical information. I hope that we have the final report from our engineer, like I said, the next couple of weeks, because our next board meeting is May 22nd. So, and I'd like for them to have that in hand so they can look through it and read through it, and so staff can look through it and read through it. And this is a real convenient venue for sharing those things with the public, but you know, we can make that available when the public wants. As far as the reports themselves, we could certainly put those up on our website, make them available. So yes.
Hang on a second, I just forgot what I was gonna ask.
Sorry. Yeah, Danny.
Hi, I just got a couple concerns. You know, you talked about Kodiak earlier, saying that they have hydro and wind.
Mm-hmm.
And right now we have hydro and diesel, and my concern is, you know, you're talking about availability of water for the city. If we get in a situation where we have a water shortage, it seems like we're gonna have a hydro shortage too. Maybe this is enough of a battery to get past that, but it seems like it would be more prudent to have an alternate style of energy that isn't hydro or diesel, whether it was solar or wind. And my second concern is, I've heard that this isn't going to bring the price of electricity down, you know, that it's not gonna make electricity any cheaper. And it just seems like if we're not reducing costs, if we're not doing something to pay for it, does that really make the project worth doing? And then the third thing, I was just wondering, you know, when you first were looking at this project, you did have a model to where you were doing similar to Powder Creek or Run of River, and how much electricity that would generate and what that would cost. And I'm just wondering if that's still a consideration at all.
Well, Powder Creek and Humpback Creek they don't have the storage element, so their cost per kilowatt hour is relatively low compared to Crater Lake. One of the reasons, honestly, that the water component is kind of important is because strictly as an electric energy source of 2 megawatt hours a year, it's pretty marginal. It's pretty expensive. So the corollary to it won't lower our rates is that it's not going to allow them to increase either. So it helps stabilize fuel prices. I mean, right now with fracking and everything, it looks like fuel's going to be pretty inexpensive for years and years, but you know, but hydro, you know, will be inexpensive. As far as the competing technologies, that's part of what I was trying to show on the technical side is there just isn't, maybe solar approaches the robustness of hydro, I don't know, but even the current technology they're saying has a 25 to 30 year life. You know, we have hydros in Alaska that have been operating for almost 120 years now, so it's a long life asset, and it provides all those resources to the grid. So if Kodiak had enough hydro, I doubt they would have installed any wind. It's just a matter of not having as much hydro resources. So, however, solar is very attractive. I mean, if I was to flip a coin right now and say, let's move forward with Crater Lake tomorrow and let's move forward with solar, I'm not so sure we wouldn't have solar on the system before we have hydro, because the costs have just gotten in range. The battery makes solar a lot better. Just the battery storage makes solar better. And so depending on how we size it. So, and then we have another hydro prospect we're looking at on Raging Creek. And as we took a closer look at that, there's some aspects of that that are attractive. That's, I think, a much more feasible hydro prospect. that is something that could maybe take us to 100% hydro. And depending on how we can work with the corporation and the tribe on funding and whatnot, there's the old log sort road, and there's a road, an old logging road that goes all the way over to Raging Creek right there. So that's a huge chunk of infrastructure that's already in place. But that's more like a 3 megawatts. That's a Powell Creek level resource, and Powell Creek provides 60% of our energy right now. So we took just a preliminary reconnaissance as we had geologists and technicians and engineers in town and had helicopters dispatched anyway. We went over and landed and just took some basic surface reconnaissance there, and we're kind of taking a look at that as well. So we are looking at other options.
Where is that?
Now that's Simpson Bay.
Okay.
So as you go up Simpson Bay, it'd be left-hand side of the right-hand arm. Do I have that right?
Yeah.
Okay. But that goes way up to like 2,000 feet of elevation, and there you get the benefits of Powell Creek plus Crater Lake. You get the volume and the elevation, and it looks like there's a fairly attractive basin part way down. So another opportunity for a project like that, and I'll use this as kind of a model. So say that you could build a large dam here that could hold a fair amount of water. Let's pretend let's say this is let's pretend this is Raging Creek and we're out of harm's way. If you have a big reservoir here, then this reservoir is getting this water, but it can't store anything down below it, right? This reservoir could collect all this water, and then you can pump it from here up to there and let it go all the way down to a power plant. And that's kind of like, that's what's nice about Raging Creek, except it might be more like midway. So you can still get this doubling effect, but you're getting it with a lot of energy, not a little bit. So, that's a little trickier to permit. If you drew a line right across the middle of where the reservoir would be, this side is native and corporation land, the other side is Forest Service land. Once you wander into federal permitting, it becomes a different animal. So, however, if you had a land swap, fortunately though, it's right on a border. So if you could orchestrate a land trade between the Forest Service and the corporations, it wouldn't create any in-holdings, and that's something the Forest Service doesn't really like. But anyway, so that's another option that we're pushing on a little bit. And frankly, when the state looked at Crater Lake, they said, why aren't you looking at that one? So we did go start looking at it. So.
Could you remind me why we didn't put an impoundment dam at Powell Creek and what the total cost of that project was and how much it's producing now?
So we didn't put an impoundment at Powell Creek because it's really poor geology. So see all this here? This is basically because this part of the mountain collapsed and slid down here. That's what the geologists are pretty sure happened. So that's kind of what happened to Powell Creek. So if you think of Powell Creek as being a long, pretty kind of a steady watershed like this, and part of the mountainside collapsed into it, that's what happened at Powell Creek. And it filled with gravel all the way behind and created Surprise Valley, and then below it you have Omen Falls. So right there at the top of that Omen Falls, it's gravel. Like, I haven't been able to put my hands back on the old 50s geotechnical report, but they estimate like 250 to 300 feet of gravel there. So it's just impossible to cut that off. That's actually one of the good things about Powell Creek. There's so much water flowing underneath it that there's always water downstream for the fish and whatnot. And frankly, we've been making a lot of improvements to the projects where we can. We've put some fish screens up there that have carried us through storms. It's saving a lot more diesel every year. We're able to reduce our in-stream flow requirement because we measured that infiltration and that water for several years and worked with Fish and Game to get that reduced. That freed up another 40,000. Let's see, what do we do? I want to say, I forget the gallons right offhand. It's a lot. 80, I could do the math here, I guess. 80 kilowatt hours, 6 gallons an hour, so about 25,000, 30,000 gallons of diesel a year. And those are very small investments for a lot of fuel savings. Yeah, Scott.
Can you remind us what the expected daily production and peak production could be for a Crater Lake?
Yes, and let me capture that, and then I just remembered I'll finish answering Danny's questions. So we built Powell Creek for $24 million total, and we got $12 million of federal funding through the Indian Energy Act, and then the state did debt reimbursement for us over about 4 years, and we were able to pay off the rest. So Power Creek is paid for. Our bus cost of power is about 6 cents a kilowatt hour, and I think our fuel savings now is close to $32 million, $33 million, somewhere in that range.
And how many kilowatts are you doing?
Since we get about 20 million kilowatt hours a year out of Power Creek, in that 15 to 20 million kilowatt hour range, depending on how much we're able to sell and how much water is available. And yeah, let me answer Scott's and then I'll get back to you. So Crater Lake is a small resource. The year-round average is about 300 kilowatts. So 2 megawatt hours, we use about 30 megawatt hours a year. So it would be somewhere between 6 and 8% of our gross system power.
Yeah, I thought your opening slide had it in gigawatts, not in megawatts.
It did. So 2 gigawatt hours, and that would be 2,000 megawatt hours.
Yeah, but that would, if it was doing 2,000 megawatt hours, then it would be providing 5 megawatt hours a day, which seems, it's well above the 300 kilowatts continuous.
Where do we go with that?
24 times 300.
Okay, so 2 gigawatt hours is 2,000 megawatt hours, or 2 million kilowatt hours.
Yeah.
So if you divide
5.5 gigawatt hours per day.
so 300 times 24 is about 7,200 times 300. So 7,000 times 300, about 2,100 gigawatt hours. So yeah, Power Creek's 25 gigawatt hours a year, so 10 times, close to 10 times as much. I'm sorry, were you next? And then
yeah.
Steve.
Okay.
Okay, Steve.
Okay, so actually, I love math,
Mhm.
so coming back to this one.
Yeah.
So you're comparing it to 2,000 grid scale lithium ion batteries. Wouldn't that be more like comparing it to 2,000 capacitors? Because batteries recharge on a faster cycle than the lake does.
Yeah.
So,
Mhm.
I mean, a capacitor.
You're absolutely right.
Yeah.
Yeah. So what Steve's alluding to is that we can charge and discharge this thing, 4 or 5 times a day, and we could do that all year long. Power Creek or Crater Lake, for example, you can't. I think with a lower dam, you have to what I call fill and spill it twice. That's an advantage for us because as a community that needs power all through the winter, and then you can let it fill up in a spring runoff, and then use all that power through your processing season, and then fill it up again in the fall rains. We could fill and spill that twice, and maybe that lets us build a smaller dam there. So there's some other nuances though. When I say life cycle, lifetime, that means that you only get 5,000 round trips out of that battery, and it's already down to, if you're at a megawatt hour and you charge and discharge that 5,000 times, you're already down to like 700 kilowatt hours. You start degrading it, so they kind of say, now does it go to 0? No, but it's not real good. It's it just, you only have so much. So Crater Lake can, that's the total resource is 2 gigawatt hours a year. So I'm also comparing 100 years of storage to 20 years of storage. But then, if you're going to replace your battery every 5 years, you got 60% of that initial $2 million cost. So you're tacking on another $1.2 million all the time. And what I'm really trying to demonstrate is that batteries are fantastic. I mean, we bought one, we're installing it, it's going to be great. It's just that, and that's going to be part of the value of it, is charging and discharging. And we're not going to, but there's another nuance here that I should point out. That's 5 gigawatt hours of total throughput, but if you don't completely discharge it and completely charge it back up, if you do shallow charges and discharges, you can get 1,000 times as much overall storage out of that. And that's the way we're going to be using it. We will do some of those deep discharges now and then when we can save hydro and offset diesel, but there's going to be other times when we're discharging and charging a little bit because we're balancing the grid. But when we're charging and discharging a little bit and keeping the deflectors open on Power Creek and delivering hydro instead of diesel, that gets us into that 6 cents versus 40 cents range. So they're just different technologies, and I'm not trying to over confuse it, but you're right. There's a lot of nuances here, and the fact is they both have big advantages. The problem with a battery is when you charge it, you have to charge it with power you've produced somehow, right? Whether it's hydro or diesel, you still have to have another asset charging it. Rain fills a lake, so that charge and discharge, there's no energy cost to it. These are just the storage costs. So, yes.
If you were to strike the words Crater Lake and put Raging Creek in there, would we be looking at how similar of a situation? It's further away, I get that, but it sounds like there's certainly no fear that somebody's going to lose lives in a catastrophe out there in the same way.
This is what Crater Lake is classified as a high hazard dam, because there are people downstream of it. There's no doubt Raging Creek, because it's a storage dam and because environmental assets also factor in, it would be what they call like a medium hazard dam. Humpback Creek, for example, is a low hazard dam. Not because there isn't an important pink salmon run downstream, but because we're really not storing anything. If that dam fails, it looks kind of like the creek just kept flowing, right? Because we don't have a bunch of water stored behind it. Raging Creek, we could wash out the creek and take out a salmon run and scour out the basin and do some damage, but yeah, it's not going to be a high hazard because, unless there's a hiker in the bottom of the canyon or something, it's not going to. So yeah.
But when
And the other thing is, I think it's safe to say that the cost per kilowatt hour, the overall project would cost a lot more, but I mean, and easily an order of magnitude more energy out of the project. So.
And who was it that was suggesting that be looked at? If you're looking at Crater Lake, you really should be looking at Raging Creek?
The Alaska Energy Authority. So, but that was their energy department, and they were looking at it just from an energy perspective. But it's a good suggestion. So, and what jumped out of looking at it is those roads that were already in place, and frankly, there's oyster farms there, and one of their biggest challenges is energy and water. So, if there's a way for us to put a little tap and help aquaculture and mariculture come along, then that's another bonus. And it also gets us a little closer to the villages. If there's more power than we need, maybe there's the transmission technology keeps improving. So. Other questions, and this is as much for me to get feedback and gather thoughts and concerns as well. So.
Well, we would all like to get 100% renewable power, or 150%, or.
But at what cost? I've thought about this project for years, Clay, and I grew up here, and I'm pretty sure everybody in this town loves Cordova as much as I do. So it's not about what I want. How much are we willing to pay to get this free energy? Nothing's free. That's a pristine, beautiful place up there. Every time I walk up there, I find peace. I see the little pebbles around the lake that, okay, so maybe not 1 million years, 10,000 years. Took a while to make that. People appreciate that. How much you want to pay to give that up? I mean, sometimes nothing is the best thing to do. You don't always have to do something. We've never run out of water. I've always had the lights on. Why are we always looking at the worst case scenarios to make a project or to keep our job or just because if you're a hammer, everything looks like if you're a nail, everything looks like a hammer. This is a bad idea.
Yeah.
Respectfully,
I appreciate that. Yeah, I'd be lying if I didn't say I don't appreciate Crater Lake for its aesthetics. And one of the benefits of this project is it's got me up there a lot, and it's a spectacular site. There's no doubt. Jenny.
I grew up in New Mexico, and we've got reservoir and dams everywhere. There wouldn't be much water if there wasn't, but it's different than a natural lake, and even if we did this and everything worked right and there was never an accident, you're still gonna have that bathtub ring effect, you know,
Yeah.
where it's not gonna look like it does now.
Mhm.
And I think everybody here appreciates the work you've done with CEC, and, you know, you pour a lot of time and energy into it, and your heart's in the right place, but I think a lot of us just worry about this particular project for different reasons, and, you know, we all wanna see CEC, succeed, and if we could have cheaper energy or have secure energy at the same time, that'd be great. But, yeah, I was kinda okay with Crater Lake until I heard it was gonna require a dam, that, you know, the levels were gonna, go up and down quite a bit, so
Mhm.
that's my 2 cents.
Yeah.
Isn't the proximity of Raging Creek sort of similar to the proximity of Terra Lake to Kodiak?
Oh, it's much closer, I think, for us.
It's
Yeah, no,
closer than Terra Lake.
yeah, and they've got to cross through mountains, and they've got 138,000 volt transmission lines that have problems. This would be a much less risky.
Mhm.
And with the road already in place and the kind of voltages and distances in our system, we could just, in fact, we're already putting plans in place. Like as we do the culvert, they're replacing the culverts at Fleming Spit. We're trying to run 25,000 volt conduits, at least have the capacity. In fact, we may replace that with 25,000 volt wire, just in case Raging Creek or Snyder Falls Creek or Crater Lake, we already have the capacity. But what we're really looking at is Snyder Falls Creek, or it's very little incremental cost for us to upgrade that wire. So that's just kind of, you know, the wire's gonna be there in 50 years. One or the other of those projects may develop in that time, so. But no, it's, we're talking about, I think Crater Lake, I wanna say it's 35 miles or something. So, you know, the left arm of Simpson Bay, when you follow that road around, I don't know, I haven't mapped it out, but maybe 3 or 4 miles. And then maybe a mile of submarine cable, and then you're at Humpback Creek, so
I see.
it's not that far, a couple miles across Nelson Bay, I guess.
All right, thank you, Clay.
You bet.
Thank
I'm not sure if it was as exciting as the choir, and I do apologize, Wendy had a good point. There's really nothing new that I've presented here, but it's just the nature of when the